Welcome, everyone. Today we have the pleasure to welcome Ben Sharp from Leeds, who is going to talk to us about Łojasiewicz-type inequalities for the H-functional near simple bubble trees. As usual, don't hesitate to ask questions, either by unmuting yourself or by writing in the chat. We'll communicate the questions to the speaker. Thank you.
Okay, thanks very much for the introduction, and also thanks to Jean for the invitation. So I hope what I'm about to say will be interesting to more purely spectrally minded people. If there's anything you're not too sure about, let me repeat, please do just jump in and ask questions. Okay, so I guess for the most part of the talk, I'll try and explain in broad terms what the different aspects of the title are. So we'll start with talking about very, very broadly what a Łojasiewicz-type inequality is. Then we'll talk about the H-functional and the questions that I'd like to pose and answer, which relate these two objects. And then the talk will take care of itself. We'll get into the details from that point onwards. So first of all, I want to talk, I realised as I was writing this earlier, I'm essentially just describing the calculus of variation. So I suppose the point of a Łojasiewicz inequality is to gain some kind of understanding about the space of critical points of some functional that you have. So it might be the area functional, you might be interested in minimal surfaces or CMC surfaces, or indeed eigenfunctions and eigenvalues, all fall into the category of understanding the critical points. But specifically with Łojasiewicz inequalities, it's about sort of understanding small neighborhoods of perhaps a submanifold, of maybe a level set of your functional. Yeah, how do we compare nearby objects? So of course that's so general as to be almost meaningless, so let me make it a bit more precise now. So let's consider some function or functional. We can just think of H as being Rn, if you like, and perhaps a submanifold, a level set of E inside the unit ball, which is a submanifold of critical points. Okay, something like that. That's the setup. Then we'll say that this function E satisfies a Łojasiewicz-type inequality if the one or both of the following are true. Either the distance, if I look at points close to this manifold Z, let me maybe draw a picture. So if this here is Z, and I'm looking at X close enough to Z, then their distance is controlled by the size, well, how far away is X to being a critical point in the sense of how big is dE of X. So in particular, well, okay, so that's the first one. And the second one is a similar kind of control. We're saying, well, how close is that? So there should be, where Z is in big Z. The difference in energy levels between nearby points to the kind of level set equally is controlled by some power of the size of dE evaluated at X. So in particular, there simply cannot be, if E satisfies these type of inequalities, and there simply cannot be a nearby critical point to Z, which is not in Z. Okay, it simply must be in Z, and it has to. They all have to have the same energy as well. So there are lots of functions which do not satisfy Łojasiewicz-type inequalities. We'll get to that a little bit more in a minute. But perhaps let me just tell you one reason why you might be interested in functionals which satisfy such things. Well, they give you uniqueness results for critical points, particularly when you're approaching by flows. So if we study the negative gradient flow for your energy function or functional, in other words, I take a point X in my Hilbert space and I walk along the steepest way of descending, walk along the vector field, which is my steepest way of descending this energy. then if E does satisfy these Łojasiewicz-type inequalities, and we have some global solution to this flow, then as long as this flow actually has a critical, has a limit point, then there can only be one limit point. So the flow gets there sort of through a curve of finite length, if you like, and the limit is critical. So let's perhaps think about a scenario where this isn't true. So if we imagine, this is a kind of standard example, and it's called sort of goat tracks. So I want you to imagine we're looking down with sort of a bird's eye view of a hill. Okay, so there's the top of the hill, and outside the height is always 0. Okay, so we're taking a bird's eye view, if you like, of the graph of our functional. So the values of our functional are pointing straight out of your screen. Then it's possible to construct E so that it's, if you like, it's what they called gradient flow lines are sort of goat tracks winding down the hill. And as they approach the bottom, they wind more and more and more and asymptote. Sorry, my drawing on these things is even worse than usual. So the gradient of our function E is sort of spiraling down these goat tracks, which are steadily taking us down the hill. And as we get closer and closer to the bottom, the amount at which the goat track is going down is getting less and less and less. And we're basically spiraling out to the whole level set at the bottom. And out here, of course, we know that gradient of E is everywhere 0. Okay, so this is an example where we do not have these Łojasiewicz estimates holding. We do not have flows which, there certainly is a whole family of limit points to this flow, but there's no way that we converge to any one of them particularly through a curve of finite length. So I guess, well, let me perhaps say a little bit more about when we do know these things. So if E happens to be real analytic, then Łojasiewicz estimates do hold. This was the first result of Łojasiewicz. So he first proved these for real analytic functions on a finite dimensional Euclidean space. Equally, if Z is an integral submanifold, so if you like, the Hessian of E is uniformly non-degenerate in normal directions to Z, this will come up again later. Then we also have these Łojasiewicz inequalities, but in general, if we just take a smooth function, there's no particular reason whatsoever that it will satisfy anything nice by the way of Łojasiewicz-type inequalities. So I guess a sort of brief history. It was Leon Simon who first extended these ideas to the infinite dimensional setting, so looking at functionals on infinite dimensional spaces, and he used that to prove uniqueness of tangent maps for harmonic maps from higher dimensional domains. And there have been, several or many noteworthy additions to this in geometric analysis over the years since then. That was back in 1983. I guess to put it in the context of today's talk, I'm going to be interested in comparing critical points, I'm comparing a critical point of a surface that has one topology to critical points of a surface which has a different topology. So in some sense, yeah, that's the basis of this talk. In what sense do we have Łojasiewicz inequalities in those scenarios? Okay, so let's now talk about the setting of the talk, which is when E is the H functional. Okay, so we are going to consider closed orientable surfaces of a constant curvature. So the functional we're looking at is conformally invariant, so this is no issue. We can always assume the domain has constant curvature. So the H functional we're looking at is the following. We take the Dirichlet energy, which is this part here, and we take off twice the enclosed volume counted with multiplicity. So if you have a simple surface looks something like a sphere, then I'm taking the Dirichlet energy of the parameterization, and I minus twice the enclosed volume. Of course, in general, a surface can kind of, overlap itself and twist around, and then you can end up counting positive and negative volumes depending on your orientation, which is what I mean by counted algebraically, etc. Okay, so you can indeed write down a formula for this V, so local coordinates, that's precisely what the enclosed volume looks like. And critical points of this functional are smooth. This goes back to a famous result of Venti, which is integral to a huge amount of geometric regularity theory these days. And amongst of course, if you just take a constant map, then it's going to be a critical point. But amongst non-constant critical points, I know that if U happens to be conformal as well, which means in local coordinates that ux1 squared is ux2 squared and ux1 dotted ux2 is always 0, then the image is always a constant mean curvature surface. So this critical points of this functional include CMC surfaces in R3. It's just occurred to me that maybe not everybody knows what a CMC surface in R3 is. So constant mean curvature means that if I sum the principal curvatures at any point, I get a constant. Okay. So a surface has constant mean curvature if whenever I look at its two principal curvatures, I sum them up, then that gives me a constant. Okay, so even studying the global picture of what are the critical points or what are the CMC surfaces in R3 is a long-standing question. So it was Alexandrov who proved that the only closed embedded CMC surface in R3 is just the standard round sphere. And Hopf conjectured that even if you allow immersed surfaces, then they can't exist anymore. The round sphere is really the only one, but that was disproven by Venti, who showed that there exist immersed CMC Venti tori in R3. And there's a huge theory it's studied from lots of different angles, interval systems and gluing techniques these days. So even just understanding, if you like, a subclass of critical points of this functional is a long story. But of course, I'm looking at it from the perspective of, well, I'm just studying any old critical points of E. So they may well not be conformal, they may well not be CMC surfaces. Nevertheless, that's the scenario we're looking at. Okay, if there are any questions at that point, I realize I've probably gone through that quite quickly. If this is the first time you've seen it, just let me know.
I have a very simple question. What does the dot on top of H1 mean?
Thank you. That's a great question. The whole thing is translation invariant, so I just take those with mean values.
Thank you.
Okay. Yeah, that was worth asking. So if we restrict just the critical points of this functional, then we know that the energy is always at least 4π/3. So in general, any old functions, you can just think, it's sort of quadratic in U here, and it's third order in U there, so you can make it this functional very badly behaved. But amongst just critical points, the energy of U is always at least 4π/3. And we have equality if and only if, well, the domain must always have been a sphere, and the parameterization it must be a conformal parameterization from the sphere to itself. Okay. So why is this? I mean, this is essentially the classical isoparametric inequality. So in this form, in terms of parameterizations, it's due to Rado, who was one of the first people not to win a Fields Medal. So what does it say? It says, well, it's the usual isoparametric inequality. The enclosed volume is controlled by the area of the boundary. Okay, so we already know what the volume looks like for maps of the form that we're looking at, and I'm sure you're all comfortable with what the area looks like. But just to remind you, we have this natural bound for the area. So the area of a surface is always bounded from above by the Dirichlet energy, and we have equality here. In other words, the area equals the Dirichlet energy if and only if V is conformal. Okay, and again, equality in the isoparametric if and only if V is parameterizing a sphere. Okay, so
I have another very simple question.
Yeah.
Is it true that there is only one such U?
No, there's a whole family of.
Yeah, but if you ask that the average is you said that the dot on top of H1 is that the average is 0?
Yeah.
Also, you have rotations as well and things like this.
Yeah, rotations, you also have Mobius maps. So if you imagine a rational map from C to itself, AZ plus B divided by CZ plus D, where AD minus BC is non-zero, you precompose, you view that as a map from S2 to itself.
Sure,
then,
but this will not change the average? Oh, you're, okay.
Actually, that's a good point. Oh, yeah, that's a good point. I don't think so, but that's what, no, it must change the average, because you can map a tiny disk. Okay, yeah, I don't know is the answer, but good question.
Sorry, thanks.
Yeah, it may well just be the identity and rotations. Yeah, that's possible. Okay. So anyway, that's the classical isoparametric inequality, and it tells us our energy is at least 4 pi over 3. I suspect that they all have integral 0 actually, but one needs to check. Okay, so let's see what this says about critical points. Well, if the thing is critical, then I can replace this by a Laplacian. I can integrate by parts, turn this into another gradient. Again, I can turn a gradient squared into something which looks like the volume. So we have this nice relationship for a critical point. This energy is simply the enclosed volume. And remember that the area is always bounded above by the Dirichlet energy. So viewing the energy as the volume for a critical point, this is the isoparametric inequality. Then I use the kind of trivial bound for the area. And again, this thing I can write in terms of the energy, and that gives us our lower bound for the energy. So it really is just the isoparametric inequality. That's all that's going on. Okay, so I guess for the rest of the talk, we're going to look at some critical or almost critical points from domains which are non-spherical. And the questions that I want to pose and answer are actually quite straightforward or naive, perhaps you might say. So let's just, so in some sense, we understand, we really nicely understand the critical points on the sphere, whose energy is close to 4 pi over 3. And now we want to look at critical points on higher genus surfaces, whose energy is close to that lowest energy level. So in this case, we definitely know that we could never actually reach 4 pi over 3. Okay, so amongst critical points on higher genus surfaces, the energy is always strictly bigger than 4 pi over 3. So one can ask the naive question, can I approach the lowest energy level through critical points on a torus, for instance? Okay, so I know a critical point on a torus will never get me to the lowest energy level, but can I somehow approach this lowest energy level? And we'll see the answer to that is no. So the second question is, well, if you take a sequence of almost critical points that reach the lowest energy level, then, well, we know for sure such things exist. They're not difficult to prove exist. What can we say about the way in which they are converging in a sense, going back to the Łojasiewicz inequality, what does the size of the derivative of E applied to UK tell us about this convergence? And what does it mean, I suppose, even? So certainly we can't have any kind of, the convergence is going to be horrible in some sense, because if the convergence were smooth, then we'd end up with a critical point in the limit, which is a map from a torus with energy 4π/3, but we know such a thing can't exist. So that's, I suppose, what I mean by blow up here. And there's a standard picture. I mean, indeed, this is one of the nicest. This functional is one of the nicest to study from the perspective of bubbling. So there is a nice bubbling theory. In other words, a sort of singular compactness theory for critical points, or almost critical points of this functional with bounded energy. And I'll talk a bit more about this in a second, but I suppose we're only going to be interested in the special case where we're approaching the lowest energy level. Okay, so let's talk a little bit about this convergence. So let's look at this bubbling theory, but suppose that we're in the setting that I'm asking, in the setting in which I've asked my questions. So suppose that the energy does converge to 4π/3, and it's a Pallas-Smell sequence, so the dE of UK goes to 0 in some sense. So Brazes and Coron says that either we have strong convergence to some limit, but as I was saying before, there's no way that can be the case unless sigma is S2, and we're assuming that sigma is not S2, so there's no way that can be the case. So we are definitely in option B. In this case, there must be a finite collection of bubbles, so maps from S2 into R3, which are, again, conformal critical points. They're sort of standard, if you like, standard parameterizations of the sphere precomposed with conformal maps from the Riemann sphere to itself, potentially of high degree, depending on what energy levels you're looking at. And what does this really mean? Because while in the limit, we're going to have some map defined on the surface we started with, and each of these bubbles is a map defined on a sphere. So that first of all needs to be explained, but at least I can tell you that the approaching energy of the UKs converges to the sums of the energies of the limits. And we can regain the omegas, if you like, or the omegas come from a rescaling of the domain. Okay, so I'll draw some hopefully instructive pictures in a minute. If you're comfortable or used to seeing bubbling theory, then this will be absolutely fine. But if not, hopefully what I'm about to say in a few minutes will help. But nevertheless, again, we're in the situation where we're assuming the energy goes to 4π/3. And we know that the energy of the UKs converge to 4π/3. But any critical point has energy at least 4π/3. So there can only be one map on this side, one non-trivial map on this side, just by energy considerations. It certainly can't be a non-trivial map from a critical point from the torus to R3, because then the energy would have to be strictly bigger. So U must be a constant, and there can only be one bubble. Okay, so the fact that we're looking at the low energy levels of these critical points means that whenever I study such a sequence that's getting closer and closer to this energy level, and it's becoming more and more of a critical point, then it has to be approaching, if you like, this, what I call a trivial bubble tree. So it must be bubble converging to a constant map on the torus and a single degree 1 bubble.
So the fact that I may have missed it, but the fact that case A is impossible if sigma is not the sphere, is that just a trivial topological fact, or is there a more profound reason for?
No, so yeah, let me explain it again, or for the first time. I don't think I did. If the convergence is smooth, then of course the energy of the limit must be 4π/3, and it must also be a critical point because everything's smooth. But there are no critical points on a torus with energy equals 4π/3. This simply can't happen. But yeah, thanks. I will draw a picture now that will hopefully not just confuse you further if you've never seen bubbling before. But we really are in the situation where we've only got enough energy to blow one bubble. Okay. So what does this look like? I realize every time I come to this blank slide that I should prepare pictures in advance and not embarrass myself by drawing horrible pictures, but I never do for some reason. So our domain is what's going on with this picture. Our domain is a torus, and we're looking at maps UK of this torus into R3, and the energy of the UKs is converging to that of the sphere. And I suppose what the Brazes and Coron bubbling theory says that there is some shrinking disk. Let's say this has radius of order 1/λk going to 0, whereby if I rescale by, whatever it is, let me just cheat. So if I let UK hat in coordinates close to this point, to u of x over lambda k, then that thing is converging to a nicely parametrized sphere. So what am I doing here? I'm blowing this ball up so that it has radius 1. But of course, I'm dragging in a little bit more as I go. So this UK hat is being defined on a larger and larger subset of R2. I'm blowing the coordinates up. So in the target, what will it look like? This small disk will basically map to almost an entire nice regular round sphere. So let me shade that in. So UK, what it's doing is it's focusing energy on this small disk. And even though that small disk is shrinking, it's sort of it's blowing that disk up more and more so that it wraps more and more around the standard round sphere. And on the rest of the torus, well, who knows? It's just converging to 0. So there's some little handle that's staying there for all k. And in the limit, well, there's really no map from the torus anymore. So let me stop doing that there. Let me perhaps say as k goes to infinity, the handle shrinks off and I'm just left with a nice round sphere. And it's being parameterized by the map omega. So remember, u hat k is being defined on a larger and larger subset of R2 as k goes to infinity. So this lambda k is going to infinity. And it's going to converge smoothly to something. It's going to converge smoothly because of the way in which Brazes Coron tell us how to blow up. It will converge smoothly to something. It will converge smoothly to a limit of finite energy, which is defined on the whole of R2. There's a singularity removal theorem and a classification result, which tells you that, well, this limiting object really is just a degree 1 conformal map from the whole of R2 into a standard S2. We should really think of that as a map from S2 to S2. Okay. So that's the picture I'd like you to have of bubbling. So I guess this is the issue really, in the sense that I'd like to compare the energy level 4π/3, which are maps from, if you like, a sphere to a sphere, with approaching maps which are just from a toral domain. So of course, there's no way directly you can compare these two maps. They live on different spaces. Okay, So let me just remind you of the questions that we started with. So the questions are, can I approach the minimum energy level through critical points on a torus? Or failing that, what can I say about the way this bubble convergence happens amongst almost critical points? Okay. So the way in which we are going to compare these things is, rather than trying to compare with a manifold of critical points, because no such manifold exists, we're just going to pick, we're almost going to do the reverse of bubbling, pick one of these bubbles up and sort of glue it back into a torus and cut it off to nearly a constant everywhere away from the bubble region. Okay. So this is what's known as dimension reduction, Lyapunov-Schmidt dimension reduction to be precise. So as I said, we want to compare maps from a higher genus surface or a torus with maps from S2. And the way we do that is literally just to glue a bubble back in. Okay, so pi, you can just think of as being the inverse stereographic projection. Okay, so we want whatever this glued in object to be away from this small, well, when we're in this small disk, I want it to look like a very, very concentrated inverse stereographic projection. So it's going to do, you know, really what we want it to do. I'm going to send a small disk to a bubble. And away from that, it's just going to be the constant, approximately equal to the constant. Okay. So that's the idea. And once we've done that properly, so the way in which we do that is really important, then if you like, what we'd like to do is study a submanifold of critical points and then apply sort of classical Łojasiewicz estimates, but we can't do that because there are no critical points. So if you like, our Z is, I think we call them almost bubbles. So they're almost critical points. So there's no way they can be a critical point. So yeah, what do we do? Well, this is a family where we have the parameter in how scaled the bubble is when we glue it in, where we've glued it to the surface, and also we're allowed to rotate in the target however we like. Yeah.
So, sorry, may I ask a question again?
Please.
What's the role of this? I think I was following until the previous slide, and now I'm a bit lost. Why is there this dimension 6 space? Can you just?
Right. So what we know, what Braze's Coron tells us is that, well, if we want to study this scenario, then we're going to have a sort of zero map and a bubble attached at the end of it. So I'm constructing a capital Z, which is approximating that that behavior basically. So they're going to be our comparison. This is like the right comparison space if we want to capture. You know, I want to say, well, this bubbling object is close to some almost critical point. Well, this is the family that we're constructing to do that. Does that help?
It does. Thank you.
Okay, great. Yeah, I'm just saying it's finite dimensional in the sense that there are lots of different. There's only a six-dimensional family of different ways of me gluing this bubble in to the surface. Okay, so again, we're only interested in maps which are sort of H1 close to this almost bubble space there. And remember, you should be thinking of lambda as being absolutely huge. These are really concentrated bubbles. And in terms of the rotation or where A is, it doesn't matter so much at this stage, although it does matter in general. So we want to try and cut off. So let me just say simply, if you try and use our methods by taking a bubble space of this form and literally just cutting off in any old way to the constant 0, 0, -1, then it simply doesn't work. You need to do it in a sort of energy efficient manner. So I guess one notices that the asymptotics of pi are very much like the gradient of a logarithm, okay? At least when lambda x are large. So at this point, what I'm trying to do is, well, I know that I want to somehow interpolate between a concentrated bubble and a constant. While doing that in as energy efficient way as possible means that I have to sort of match the asymptotics of pi in a small ball with a harmonic function, if you like, on the exterior of the ball. And the highest order term looks like the gradient of a logarithm, i.e. the gradient of a Green's function. So let me write it in a weird way. And then notice that on a surface, the Green's function, at least in local coordinates, and of course we only have to what's the word, glue it in a local region anyway. In local coordinates, it really does look like a log. But of course, the Green's function isn't globally exactly a logarithm, because this function doesn't make sense. So we have to include this corrector function, so that in our local coordinates, the Green's function really does look like this. So I suppose all I'm doing is trying to interpolate in as energy efficient way, and noting that the asymptotics of a bubble are kind of like the gradient of the Green's function. So that's what we're going to use to cut off. So actually we have to perturb our bubble a little bit by even over the bubble region by the gradient of the regular part of the Green's function, in order that this nice kind of harmonic extension, if you like, makes sense globally. So this is what it looks like close to a point P. It's just the usual map that you'd be interested in your coordinates, and then you have to add in this little smooth corrector function, which is, well, J is smooth, so this thing is well controlled, and lambda is large, so it's a very, very small perturbation, but away from the point, it really is just the three components are just given by the gradient of the Green's function. So this is really crucial to sort of home in on the behavior of our energy functional on the scaling parameter, if you like. So it makes the energy functional with this definition, it makes it feel the scaling. In the sense that if we defined it via an arbitrary cutoff, then I wouldn't get this lambda to the -2 term here. I'd have to jump right to a lambda to the -3, and that just doesn't seem to be enough. Okay, a bit of a mysterious comment at this stage. So again, mysteriously at this stage, it's crucial that we have this lambda to the -2 term in our expansion, and also that comes with a non-zero coefficient, okay? So this function J, if you like, is this mixed second order derivative with respect to the two components of the Green's function. Really, it's the same. Well, let me come back to this at the end. I realize this is very mysterious and perhaps annoying that I'm not explaining this, but I'm happy to explain it if people want more details at the end. But essentially, one can prove using a bit of complex analysis or Riemann surface theory that this term J is always strictly negative. Okay, so that's precisely what it is. In fact, it ends up being a sum of sizes of holomorphic bond forms. Okay, so this is slightly mysterious, but by gluing carefully, all I want to tell you at this stage is that it gives us a nice term in our expansion which feels the lambda component, feels the scaling. Okay. Okay, so I suppose perhaps the most standard crucial fact about Lyapunov-Schmidt reduction is that our energy is invertible in normal directions. Okay, so what do I mean? I mean that if I just look at the orthogonal complement of the tangent, let me draw some pictures. So if this is our Z here, and there's a Z there, and I look at the orthogonal space mu Z, then the Hessian of our energy functional is invertible in the normal directions, means that if I restrict the Hessian to this normal space and look at the eigenvalues, then there are no eigenvalues near zero. Okay, so the only way of me getting a Jacobi field, if you like, or an almost Jacobi field, is to actually move along Z itself. So in some sense, this is an integrability condition. If I could spell integrability, it would be. But let me perhaps, rather than going into the calculations, heuristically say what this gives. So we know that capital Z are by no means a collection of critical points. They're sort of almost critical points. So this, since d squared E, when restricted to nu Z, is invertible, it tells us that we can, by implicit function and there's an implicit function theorem argument, but it's not a straightforward one, or it's not an obvious one. We can solve at least along somewhere along nu Z. We can solve dE of, let me call it W, perpendicular is zero. Okay. So because the second derivatives are invertible in normal directions, then I can really find nearby critical points, as long as I restrict to the normal space and I only ask that the dE vanishes in orthogonal directions. Okay. So if you like, there is a family, there's a close by family, let's call it Z tilde, where if I look at dEu in Z tilde, then this is almost tangent to Z. Okay, we can sort of locally solve the orthogonal problem. So this is where the reduction to finite dimensions really helps out, because it sort of suggests, in order to understand the critical points or almost critical points in a small neighborhood of Z, I only really need to understand the behavior of our energy functional in tangential directions to Z, which is a finite dimensional problem. Okay, so that's the heuristics of dimension reduction. Okay, so this non-degeneracy condition effectively allows us to ask questions about, well, can I find nearby critical points, or can I not find nearby critical points, or what's the behavior of nearby almost critical points? It sort of becomes a finite dimensional problem, because I know I can always solve the normal problem, because this thing is invertible. Okay, so that was a very hand wavy explanation, but again, welcome to ask me more questions. So let's now use this in a sort of hands-on way and see what we can say about points which are close to Z. Okay, so I'm going to look at a point U which is sufficiently close to Z, which means that there is a W in nu Z, so that W is U minus Z. Okay, so I can use this non-degeneracy, split W in its positive and negative eigen direction. See, I am talking about spectral things, I suppose. And then estimate, well, a little bit of implicit function theorem. So there's a trick here, right? So I've written W, first of all, in its W plus and W minus component, and then I've taken its W plus minus W minus component, again, which is normal. Using the fundamental theorem of calculus a couple of times, I've rewritten this difference, and what do we end up with? So here, I guess I'm assuming that there's a uniform estimate on three derivatives of our energy functional. Okay, because I'm estimating the difference of two derivatives. Anyway, the upshot, well, I suppose I'm not expecting you to follow that in real time, but really I'm just letting you know that all I'm doing is applying a bit of linear algebra and the fundamental theorem of calculus. And we end up with the following, right? So because W is small, U is close to Z, I can absorb one of the terms and end up with this inequality. That is controlled by that. Or in other words, the distance from U to Z is controlled by the derivative of E at U, but also I have this time I have this derivative of E on the manifold Z term, right? So remember, if this were actually a genuine manifold of critical points, then that would go away, and this really would look like a Łojasiewicz-type estimate that we'd started with. Okay. So again, there's not much on the next slide that I'm expecting to be followable in real time, except to remember that perhaps we have this expansion that the energy of Z lambda was 4 pi over 3 plus J over something like J over lambda squared. So that if I were to estimate d by d lambda of that, then I get a lambda to the minus 3 term, which I know has a strict bound. Again, I can manipulate these things with fundamental theorem of calculus, simply estimating error terms and yeah, I mean, almost exactly the way it's done up here, absorbing differences through higher powers of W to get this term. But also what I've used in this calculation is simply the behavior. So also used the behavior of E restricted to Z. Okay, so if you like I said before, the heuristic is we only really need to understand the behavior of E when it's restricted to this finite dimensional manifold, and you really can just estimate, you know, the sizes of first derivatives when restricted to Z, the size of second derivatives when restricted to Z, and essentially hope that you can pinch the right terms and absorb the right things in your expansion. Okay, so there's nothing, I suppose, deep per se going on here, but the moral is really that because the energy is invertible in normal directions, we really can reduce it to an analysis on a finite dimensional manifold. And when we couple that with the sort of the fact that the fact that our calculations, if you like, show that the d by d lambda directions are asymptotically significant, then this in fact really does force us to prove that there can be no critical points close to the manifold Z, right? So essentially, if there was a critical point close to Z, then this is telling me that lambda would have to be infinity, but that's obviously complete garbage. It just can't happen. So we already know, we've already proven actually, just with a bit of, okay, so I haven't given you all the details, of course, but let me give you a few more. Using the invertibility of this thing in normal directions, the fact that we have a significant tangential behavior, the scaling is kind of asymptotically significant, and the analysis of E restricted to this finite dimensional space, then we're in fact able to control the scale of our bubble by the size of the dE of U. So if U is very close to being a critical point, then it must be a highly scaled bubble. And as dE goes to 0, that tells us exactly how the bubble scale is going to infinity, I guess. Okay, so that was all mostly morals. But let me spend a couple of minutes. Oh, I think I'm probably going to finish early. So I'll talk about there's just two theorems I want to talk about. So the one I just mentioned, which is that we really are immediately able to show that there are no critical points on a torus, for instance, close to the lowest energy level. That simply can't happen. So there must be an energy gap. And we have a sort of, oh, that's an interesting comment. So, yeah, so if I allow the conformal structure of the torus to degenerate, then this is no longer true. So it is possible for me to, if I consider this as a functional of both maps and metric, then I can effectively shrink one of the geodesics on a torus and find a family of critical points along these, these degenerating tori, which really do approximate a sphere in energy. So these will look like, something like really a sphere, but I want this to actually be a torus, so I drill a small hole from the north to the south pole. So there are, Venti has shown that there are critical points on a torus, which look like this, so a very, very thin net. But if you fix the metric on the torus, then there is an energy gap. So yes, on that fixed torus, very degenerate torus, there's a critical point whose energy is close to 4 pi over 3. But if I want to find it on that fixed torus, one with lower energy, then it won't exist. However, if I make the torus a bit more degenerate, then I can get a bit closer to 4 pi over 3. Anyway, there's still some, my point is there's still some analysis to be done, even in this very naive kind of situation. And the full theorem on this paper is that we have the kind of the standard Łojasiewicz-type estimates, even though perhaps odd powers on the right-hand side. But again, this tells us immediately that there can be no critical points close to Z on a fixed domain. But also it tells us something about how far is U from Z, how concentrated is U, depending on its on the size of its derivative. How far is its energy from 4 pi over 3? So potentially these things could be used to study kind of flow rates for H surfaces. That's not my individual motivation. My individual motivation is sort of, I'm interested in more, I guess, more complicated questions about the structure of higher energy critical points and really trying to say something about CMC surfaces in R3. I suppose you can think of this as being, from my perspective, as being a first step in that direction. So I'll stop. It's 54. I guess you're asking people to stop at 55. Is that right? So I will stop, but then I'm not going anywhere. So if people have questions, then I mean, at least if I stop, you have the option to leave. Right? So thank you very much for your attention.
Thank you. So thank you very much, Ben, for the nice talk.